chemistry heroes here. We know that the difference between a word equation, a formula equation, a chemical equation. We're moving on to balancing. We're going to skip a couple of slides. I would like you to look at page 246 in your textbook, if you would be so kind. 246 in your textbook. What you're going to see there is a list of symbols used in writing equations. And aside from what the notes say, you are responsible for first three. So the straight ahead arrow yields. You're responsible for the reverse arrow, the double arrow. You're responsible for all the state signs, the representations of states, which I guess that's the same thing. The little s, little l, little aq, little g. You're not responsible for the up and down arrow. Those indicate a precipitate forming, and they precipitate something coming off as a gas. You're not going to be responsible for those. We're just going to use the state signs. You're responsible for the reactants being heated, the little triangle over the arrow, or the word heat. And you are not responsible for those last four. So, oh, actually, no, you know what? You should be responsible for temperature of reaction. Yeah, you should. So that's the second one from the bottom, temperature at which the reaction is carried out. Yeah, so add that to your little list. Okay, those are really useful, and we're going to talk about a few of those as we go today. So, what's so important about chemical equations? Well, next chapter when we get to stoichiometry, we're going to be using a balanced chemical equation to start every single problem. Sometimes starting from a sentence. So you have to do all the things you learned in chapter 7, and then all the things you learned in chapter 8, and then all the things you learned in chapter 9. It's cool. You're building a staircase. Chemical equations show you the relative amounts of the chemicals that are reacting. So if you look at the equation we've got there, H2 plus Cl2 yields 2HCl. We can say that that's 2 molecules of hydrogen reacts with 1 molecule of hydrogen reacts with 1 molecule of chlorine to produce 2 molecules of hydrochloric acid. We can say that. We could also say that 1 mole of hydrogen reacts with 1 mole of chlorine to produce 2 molecules or 2 moles of hydrochloric acid. There's something we can't say, though. We cannot say 1 gram of hydrogen reacts with 1 gram of chlorine to produce 2 grams of hydrochloric acid. Why not? Don't yell it out. If you think you know, jot down your notes to yourself in your notes. Why can we can say 1 mole of hydrogen and 1 mole of chlorine produces 2 moles of hydrochloric acid, but we can't say 1 gram of hydrogen and 1 gram of chlorine produce 2 grams of HCl. All right, somebody who has on a drawstring somewhere. Wow, are we really hoodieless today? You've got a drawstring. Oh, okay, we got 3 people with drawstrings. You can coordinate. I can see your mom, David. Get it out.
Oh, that's actually not good.
I don't know.
Sucks, doesn't it? You don't know what it sucks. Do you? No, come on, baby. It's like a lot of shame up there. It's terrible.
Yeah. Okay, why not? So, okay, have our drawstring people come up with any ideas? Give it a shot. Anyone dressed up? Here we go.
How about anyone with really long dressed up?
Yeah,
I don't like that.
anyone with hair longer than that.
Okay, so someone wearing a tie. Okay, Christian, give it a shot.
The atomic mass units don't match up with the AN units of 2HCl.
No.
There's a gram of hydrogen. There's a lot more hydrogen in 1 gram than there are.
Yeah, exactly. Does 1 gram of hydrogen have the same number of pieces of hydrogen that a gram of chlorine does? No. I mean, hydrogen, 1 mole of hydrogen's got a mass of 1.01 grams. That would be 2.02 grams. 1 mole of chlorine molecules is, what, 35, roughly 70.9 grams of chlorine. Yeah, the number of molecules and atoms don't match up. So those relative amounts that are shown by the coefficients can represent molecules or atoms or moles. They can't represent mass. They're relative masses. So this is a lot. Has anybody here ever made salt dough at home? If you have little siblings or little cousins, this is a really, I'll be doing this with my daughter this year or next. It's a fun little project. So you take, I think it's usually 4 parts flour, 1 part salt, 1 part water. So it doesn't matter if it's a teaspoon or a cup or, a quart jar. It's parts, it's relative amounts. So you mix them all up and you get Play-Doh basically, and you can make little prints. Yeah, salt dough. And most little kids try to lick it because it tastes salty. So anyway, they are only relative amounts though, but that's important, and this becomes critical in stoichiometry. You're going to use this as the foundation of every problem you do in the next chapter. Okay, we can figure out what mass of something will be produced using this equation. This is basic stoichiometry. We're not actually going to go through the sample on 249. Can you figure out the mass of 2 moles of water? Of course you can. You know how to do that. And we'll do that a lot in the next chapter. So from those relative masses, we can figure out an actual mass for each of the reactants and for the product or products. Now, this is interesting. Reversible reactions. So that second symbol on page 246, the little double arrow. Some reactions run forward and backward. It's crazy. It's wild and crazy. So let's imagine we've got the equation 2H2 plus O2 yields 2H2O. So we take hydrogen gas, we take oxygen gas, we put them together, we get water. Can we take water and bust it apart into hydrogen gas and oxygen gas? Yes, we can. So we can run that reaction both directions. That's all it is, a reversible reaction. Now, a couple important things about reversible reactions. Not all reversible reactions will run, period. And not all of them will run without some input of energy. So in the example of hydrogen and oxygen gas forming water, hydrogen gas and oxygen gas will form water with no encouragement from you whatsoever. You put the 2 of them in the same room, they're going to form water very often. To break water apart, however, requires a push. It requires some energy. We'll talk about that specific example a little later. You can write a chemical equation for something that's never going to happen. Like I said, I could write, we dropped aluminum in water a couple days ago. Remember that? Did it do anything? No. The aluminum in hydrochloric acid did. Could I write an equation that says that aluminum plus H2O yields aluminum hydroxide plus hydrogen gas? I could write it down. Not going to happen. It's kind of a waste of my time. So you have to be careful, and we'll talk on Wednesday of next week about activity series and why reactions run or don't run. You can determine the amount of products and reactants in either direction if it's reversible. So that's all we need to know there. All right. How many of you, if I asked you on a scale of 0 to 5, so hopefully you've had some time to you're probably about halfway through that sheet, that worksheet, hopefully. Because if I released you, you were on your own to do that. On a scale of 0 to 5, where 0 is, I don't know what chemicals are, you're not speaking a language I understand, and 5 is, I can do most of these, without thinking about it. Where are you at? Okay, I got 3s and 4s. I got 4s and 5s. I got a lot of 3s and 4s. Good, this is where the other class was. So what we're going to do is we're going to walk through a few reminders and walk through a few more together as a group. And hopefully that moves any of you who are still at the 3 up to a 4, and those of you who are at a 4 up to a 5. So we just want to shift it a little bit. And if you're still at a 4 and you've got a couple days to get to that 5 before we FIP you. We FIP you on Monday. Okay, let's FIPing chemistry. I guess that does sound a little dicey, doesn't it? All right. Balancing equations. This is the thing we did yesterday. I'm just going to walk back through the steps. When you're given a sentence that describes a reaction, the first thing you want to do is write the word equation. Right? What are your products? What are your reactants? Put in your symbols, and then write formulas. I will tell you that in the other classes they were working on stuff, and this is common. Most of the people who were stuck on balancing had bad equations to start with. When you get onto the back side of that sheet where you're writing all the formulas, it's really easy to screw those up by not writing the correct formula. And then it'll never balance because it's not an actual reaction. This is what we did yesterday, but we'll talk about it again. Balance one kind of atom at a time. And if you've got something that appears in a compound on both sides, get that balanced first. Get that balanced first. If you've got something that's in a compound on one side and all by itself on the other, do those second. And then if you've got things that are, well, hydrogen and oxygen are your big examples, do those last. Because those very often are appearing on one side all by themselves, and they're the easy thing to fix at the end. Polyatomic ions. We're going to do an example with this on the board. If you have a sulfate ion on this side, and you've got a sulfate ion on this side, and the sulfate ion didn't break up, you don't have to balance your sulfur and your oxygen independently. You can balance sulfate ions as a unit. We'll do some examples with that. Okay, when you're done, count up, count your atoms, and if your coefficients can be simplified, simplify it. If any of your coefficients is a 1, or if there's no coefficient in front of something, you can't simplify, because you can't go to half. But like if you've got 2, 4, 2, 6, you can simplify that. Okay. The biggest single error in balancing is having a bad formula. Having a bad formula will completely wreck your balancing. And I don't think any of you would ever do this. It's too horrible to even contemplate changing subscripts in order to balance. You can't do that. Because you're making a whole new chemical. And then it's just a lie. It's a big lie. So, yeah. Okay? We're going to do some practice with balance.